So this talk is about some ongoing work that we're doing, and we're trying to build something called a zero knowledge middle box. And in a sentence, what this is a framework to enforce that allows a middle box to enforce policies on encrypted traffic without actually decrypting the traffic. And we're going to use this technique called zero knowledge proofs for that. So this framework is best explained with the main example that we have, which is DNS filtering. So suppose we have a client who's in a local network, say a campus network or a corporate network, and this client is making a query to an external DNS resolver. And because he's in a local network, all of their queries go through a middle box. And the middle box will just forward the query to the DNS resolver. But when it wants to perform filtering, the middle box can just check if it has, say, a block list of banned queries. The middle box can check if the query that the client made was valid or not. And if it was not valid, like it's a part of some block list, it will drop the query, or otherwise it will let the query through. So this has been like a standard DNS filtering application that you could do on unencrypted DNS. But once you encrypt the DNS, this is a problem, because when the middle box only sees the encrypted query, it's not very clear if it's possible for the middle box to actually check if the query can be is valid or not. And this is a problem. This is an issue because for the client's privacy, the client wants to encrypt the query. But for the network's policy, the network wants to read the query to check if it's a part of a block list. So because of this, there seems to be an impasse, and there doesn't seem to be any meaningful compromise yet, because the network does need to look at encrypted messages, because, for example, in the US and in UK, it is legally mandated for schools to block certain content, and because of that, they need to read the DNS requests. So what our goal is in this project is to find a solution that would give the best of both worlds. It would protect the client's privacy while also allowing the network to monitor the traffic. And how our solution is going to look like is this. We want to give the same encrypted query, just like normal, but the client will attach a proof to the query. And this proof will have a special verification algorithm where the proof basically says, the encrypted query that was attached with the proof is not a part of a certain block list. And if the verification algorithm passes, the middle box will forward the query to the DNS resolver. Otherwise, the middle box will drop the query. So the goal of our work right now is to address this verification. How do we design a verification algorithm? How do we design a proof system that works like this? And also, one thing to note is that the DNS resolver, nothing changes for it. It's completely oblivious to the fact that this encrypted query was sent with a proof to the middle box. This is just changes are only required at the client and the middle box. And in fact, this is really important for us because we want to work with TLS 1.3. We don't want to suggest any modifications to TLS, or we don't want to use a new encryption algorithm or anything. So we want to work with that, and that is one of our main priority when we are building the system. So we're going to use a tool called zero knowledge proofs, and I'm going to have to take a bit of a detour to explain zero knowledge proofs over here. And it's best explained with an example. So suppose there's a prover and a verifier, and they have a Sudoku puzzle, and the prover wants to show that they know the solution to the Sudoku puzzle. And the easiest way to do so is just simply revealing the solution. The verifier and the prover look at the solution. There's some Sudoku testing algorithm. They pass it through that, and it'll either accept or reject. But what if the prover doesn't want to reveal the solution? The prover wants to hide the solution, but just convince the verifier that he did know a solution. And that is done through a zero knowledge proof. So you can think of it as some sort of black box that encapsulates the actual Sudoku testing algorithm. So what this zero knowledge proof does is it gives the puzzle, and it also takes the puzzle and it takes the solution, and it produces a proof. And this proof is basically claiming that the prover who created me knows the solution to the puzzle that was presented here. And the verifier sees the puzzle and the proof and either accepts or rejects. And this basically depending on whether if the verifier is convinced that the solution really was a valid solution or not. And the zero knowledge name comes from the fact that the verifier never sees the solution. The verifier only sees the proof and is convinced if the proof was if the supposed solution was valid or not. And that's why it's called a zero knowledge proof. And we want to try to use this for the DNS filtering application. So why this is very interesting right now is that zero knowledge proofs have been around since the 80s. But over the last decade, there have been many practical, near practical constructions, depending on the application, that have been using zero knowledge proofs. And there are many frameworks that kind of work in this general format. You have any algorithm you want to test, and the algorithm takes some sort of private input. Well, the zero knowledge proof will give you a proof that the private input passed the test without actually revealing the private input. And there are many compilers that will take any general testing algorithm that you write in a high-level language. It'll compile it into a zero-knowledge proving algorithm and a verification algorithm. So we want to use this for the TLS application. So our goal right now is to design a zero-knowledge proof statement that will work for the DNS filtering application. Okay, so here's the first attempt at this. We know that the client gave an encrypted query. And how about sending the private input as the AES key that was used to encrypt the query? Suppose we're using AES. Using the encrypted query and the AES key, you run the decryption within the testing box. You get the URL after you decrypt it. And using the URL, you have to check it against a block list, and you'll produce a proof that this URL was not a part of the block list. So over here, now the middle box will just take the encryption of the query, the encrypted DNS query, and it'll see the proof, and it'll either be convinced or unconvinced that the underlying URL that was queried was not a part of the block list. And this is zero knowledge because the middle box doesn't actually learn anything about the key or the URL. It only sees the proof, and it doesn't learn anything further than that. So this would actually work for us if we had a setup like this. There are some details that we need to fix over here. For example, the block list we'll be representing using Merkle Trees, where you take all the URLs in a block list and write them in sorted order as the leaves of the Merkle tree. And just like a Merkle membership proof, you can write a Merkle non-membership proof. And it also scales logarithmically like a Merkle membership proof. And so the root of the Merkle tree will be given as a public input. The private input would be the Merkle non-membership proof, and this could be verified. But there is one further issue with this, and that's regarding the key. So there's this issue that we're calling key equivocation, where since like TLS uses the most popular one is AES, there's also Cha-Cha. You can take any key to decrypt any ciphertext. So for example, if the real key would have decrypted the query to an invalid, so the URL was actually in the block list and should have been blocked, well, you can actually just try out different keys, find some fake key that'll decrypt the same ciphertext to a different URL that is not a part of the block list. And so the underlying issue really is that TLS 1.3 doesn't support any committing encryption schemes, which would committing encryption scheme would have prevented a different key to be. It can only allow the ciphertext to be opened in one way. So you can't use a different key and then open the ciphertext in two different ways. So to solve this key equivocation issue, we'll take a quick look at TLS 1.3. So TLS 1.3 has a Diffie-Hellman key exchange. So the client and the server, they perform a handshake. All the messages go through the middle box again. There's a Diffie-Hellman key exchange, which produces the Diffie-Hellman secret. And there's something called a key schedule, which is just a series of hashes that you do. You process the Diffie-Hellman secret to get the final key, the AES key that you'll be using for the application data, the DNS. So how this would work here is the key schedule. This is a big diagram, but basically you take the Diffie-Hellman secret that was performed. All these arrows are just a series of SHA hashes. You keep hashing it, and you get the key over here, which you can extract. And this is the key that will be used for the application data. So long story short, what we need to do is we need to rerun part of the key schedule, but we don't have to start with the Diffie-Hellman secret. We can start with some intermediate secret called the handshake secret. Again, the details aren't really important, but the final thing is we need to repeat a part of the key schedule to make sure that the key that we'll be using in the zero knowledge proof box is unique. So we have the handshake transcript as the public input. The private input will be a secret from the key schedule. And it will be this key schedule secret is kind of unique. Like for every key schedule secret over here, you can only get one key. And because of that, it's binding to the key. And if you use a different key schedule secret, the handshake secret, it will reject. The key schedule will not work out. So just again, like a really quick diagram of the key schedule secret is that of all the many secrets in this path, one of the secrets is sufficient to obtain the binding that we need. So here's our final zero knowledge proof statement over here. We have the key schedule. We'll actually run part of the key schedule. We'll run part of the key schedule and we'll get the key. And using this key and the DNS query that was encrypted, we can decrypt it within the zero knowledge box, the black box, and we'll get the URL. And with this URL, we can run a Merkle non-membership proof and prove that the URL that we queried was not a part of the block list that was specified. And this will produce a proof. And again, this proof will be verified by the middle box. And so the middle box never sees the URL, never sees the key, but is convinced that the encrypted query was not a part of the block list. Yep. So this is our, in one picture, this would be the zero knowledge proof procedure over here. So, but the interesting thing that we really want to also highlight over here is that we can run any sort of policy test over here. So if the client sent an encrypted message, and this encrypted message could have been for any application, not just DNS, what our framework kind of allows is for you to decrypt the message, but in a very private way, inside the zero knowledge box. And you get the plain text of the message. And then you can run any policy test that you want here that you can define. For example, we've done DNS filtering. We've also done a HTTP firewall and an ODOH resolver allow listing. But other possible applications are malware scanning and data loss prevention. So if you can write any sort of test here without revealing the plain text of the message, you can prove to your network middle box that your message satisfied that policy. So this is sort of the goal that this is what we have been able to get, and this is how our framework works. So we do have to talk about performance. And in terms of performance, well, let me first talk about the implementation. We constructed these zero knowledge proofs using a library known as XJSNARK, and the proofs are generated using a library called libsnark. So these, and this is GROT16 is the algorithm that is used. So this would be familiar to people who know a little bit about zero knowledge proofs already. But just to understand the performance, again, let's go back to the operations of the key schedule of our zero knowledge proof. So we do the key schedule part of it. We do the decryption. And so the key schedule is just a series of SHA hashes. And it's about 40 blocks of SHA, the key schedule. The decryption involves just AES. We're using AES. We can use any cipher that TLS 1.3 supports. The Merkle proof, we're using a special hash function called Poseidon hash function, which is very friendly for the zero knowledge constructions that we're using. And we've tested our implementation on a block list that has 2 million entries. So here's how the performance looks. So again, the process is that the client sends a query with the proof to the middle box. Well, here's the good news. The good news is that the verification time is very fast. It takes under 5 milliseconds to verify a proof. So the middle box has very little latency on that end. The proof size is also very small. It's just 300 bytes. However, the proving time for a client to generate a proof at the start is just 20 seconds, which is really makes it impractical for a low latency application like DNS. But this is where we've found some improvements in how we use the proof, which we'll explain later. But just to, and also something interesting is that most of our running time is really in SHA-256. Like if we could find a way to run zero knowledge proofs on SHA much faster than we have right now, this number it'll be much faster to generate proofs. So how are we so this 20 seconds, we found a way to amortize the proof over the entire session. So it turns out this 20-second TLS channel opening proof, which is what we're calling it, This can be done at the start of the TLS session. And once the session's opened, the remaining proofs can sort of reuse the first proof, and they're much faster. They take just 6 seconds. So again, so the first proof to open a channel will take 20 seconds. It goes through the key schedule procedure, and the remaining proofs will reuse the proof and it'll be much faster and takes just 6 seconds. And another good thing is that this opening proof that took 20 seconds, it can be done in the background. You just need to open a TLS session with a DNS resolver, and you can maintain their channel. You could maintain the session, and sessions could live for like few hours to few days. It can be open for as long as you need. And even if you are making multiple sessions to multiple servers, you can just run it in the background, and it doesn't affect the DNS latency that the user observes. So this 20-second proof can be done once in the background whenever the client opens the computer. It can be maintained. And the rest of the messages throughout the session will have a much shorter proof of 6 seconds, which again is still low, but there's a lot of promising improvements over there. So just about future work, of course, one of our priorities is to optimize the proving times. There are many zero-knowledge libraries and algorithms that we can try out. There are also other plug-and-play optimizations within TLS. For example, when we moved from AES to Cha-Cha 20, the amortized proving time of 6 seconds just went to 4 seconds. So it is a very significant speed up because Cha-Cha has an algorithm that structures more favorable to representing it in a zero-knowledge proof than AES. Some other applications we're looking forward to is we want to support private block lists. And we also want to think of other policies that would fit well with our middle box framework. Because we can plug it in. This is just DNS filtering, which is, again, it's a very low latency application. But even there might be other applications that will fit well with our zero-knowledge proofs. So, for example, data loss prevention is one thing is one other application. We've done HTTP firewalls as well. And it's all in the paper, so it's up on ePrint. And we have the implementation that all the code is available on GitHub. And that would conclude my talk. Thank you.
Wow, that was great. And we have a lot of questions already. So if you can take a look at them and answer whatever you want.
Hi. Okay. So yeah, I'm looking through them. And one of the questions is if there was a key committing AAAD for TLS 1.3, then the key schedule commitment would not be required. Yeah, that's true. We don't have to go through the key schedule if we had a key committing scheme. TLS 1.2 had a committing encryption scheme, but 1.3 does not support anything. If you could change any of the details or wire formats of the protocols like TLS, how would you change them to make the application of these zero-knowledge proofs easier? Well, again, the biggest issue for us is really a SHA, and SHA structure is not very favorable for representing in a zero-knowledge circuit. So using another hash would be much easier for that. That would be like, it'll make everything much faster. Like it'll bring it down to 5 seconds. Have you considered HTTPs want to use the content structures of the underlying plaintext? I think that is similar to the AEAD thing. I'm not sure what the specific policy would be, but I can talk about that in the channel. If the user could send a fake AES key, is there a reason they can't send a fake handshake key that drives the correct AES key? No, we were able to prove that you cannot send a fake handshake secret instead. The handshake transcript is public, and there's only one handshake secret that will even accept, like there's a test within the key schedule, and it won't pass with a fake handshake secret. Does the prover need access to relevant block list to generate the proof? Yes, that is true. So the prover does need to know the block list to generate the proof. One of the things that we want to implement in the future is to make the block list private. So in our current construction, we need the prover to know the Merkle tree of the block list. But many like DNS resolvers, they don't want to, it is kind of like proprietary information, all the block list and the sites that they've collected. So they don't want to reveal the block list to the public, but there's still ways, like there are many accumulator schemes where you can prove that your URL is not a member of the accumulated set without actually looking at the entire set. Is there an implementation not based on Java, Rust? Yeah, that's what I'm working on. Like we are working on building it in Rust, and it's much faster than Java. Because there are many like libraries like Bellman in Rust that build snarks that are have a better proving times than this. For a home setup scenario, suppose ZK goes into the DNS middle box. Would the performance of generating the proof be on good things like? Well, generating the proof will always be kind of tough because I think that is the bottleneck. I'm not sure if things like Raspberry Pi would be like something that, because we tested our things on like a 32 GB RAM Ubuntu server. So I'm not sure it would be easy on a smaller system. But that is also one thing that in general, like the area of zero knowledge proofs, people are really working on getting proofs to be as efficient as possible and to make it much easier to generate proofs. I think it's a very active area of interest, zero knowledge proofs right now. So we're that's why we think that DNS is a pretty good application for that. So Frank, I think I've answered all the questions over here. I'll be happy to like chat with people in the questions section if that's okay.